Hey everyone, thanks for coming. Today I'll be talking about our work on high performance, durable data structures with minimal ordering constraints for persistent memory. And this is work that I've done with my advisors, Mark Hill and Mike Swift at the University of Wisconsin-Madison. So persistent memory offers the best of both worlds, memory and storage. And so different people, including the ones in this audience, see different things, right, when they look at it. Some folks just care about storage, and all they see is a faster file system. Others care only about memory and they see a bigger DRAM, and that's fine. And then there are some of us who care about both of them, and we see the promise of recoverable applications with durable in-memory data structures. And so I'll be focusing on the last of these in this talk. And our vision is that we want to help programmers who want to build such recoverable applications. And so we believe we should expose durable data structures and hide all of the grimy details of persistent memory like logging, ordering, fences, flushes, and all that. Because the average Joe programmer doesn't really care about software transactional memory. They care about writing the logic of their applications, and that's where we must help them. And so yeah, we must build libraries that have efficient, durable data structures that look somewhat like C++ STL that's widely used today. And they can just use these data structures to build whatever applications they want or they care about. And the kinds of data structures I'm talking about are similar to the containers that you have in STL, right? Where we don't give them a B plus tree, we give them a map, a set, a vector, a queue, or something of that sort. So this is where this talk will focus on. So briefly, the outline of this talk is quite simple. I'll set some context for the work we've done, analyze some of the overheads of durability on real Optane persistent memory that we've observed, talk about our mod data structures which are minimally ordered and durable, and then finally end with a brief evaluation. So most of the people who are in the audience are familiar with this, so I'll kind of rush through all of it. But typically, programmers who care about persistence of their data have to worry about durability, crash consistency, and failure atomicity. And these problems arise because an application's data can be in many places, most of which are volatile in today's systems. And so programmers have to explicitly move the data from volatile caches into the so-called persistence domain using a combination of CLWBs and S fences. And they have to make sure that the ordering is correct so that they don't end up with a partially updated data structure. And if you want to compose different operations to multiple data structures, you have to do it in a way that's atomic with respect to failure as well. Currently, the state-of-the-art approach is to use a software transactional memory library like Intel's wonderful PMDK to handle these three properties. And so let me show you a code example of how that would look like. We have an array or a vector which is durable and stored in persistent memory. And we want to perform a swap operation. So we want to change the locations of x and y in this array. So this typically involves two different operations, right? We have to write x to the location of y and then write y to the current location of x. And we want to make sure both of these updates are atomic with respect to failure and each other. So starting at the top, we are using an STM library. So we read in the two values at the indexes that we want to swap. Now, before we overwrite any data, our STM library does all of the hard work of creating a log. It writes either the old value or the new value, depending on what kind of logging mechanism you have. And it makes sure that this log is durable in persistent memory before it actually overwrites the value and destroys it, right? So we now have this log which has made it out to persistent memory, and the program can go ahead and overwrite the old value of x with y. And we can do the same thing for the second update that we want to do, which is to overwrite the value of y now with x. And let's assume that we crash at this point of time, right? The caches are volatile. And so what this means is that we are going to discard all of the data that's there in the caches at this loss of power. And the only thing the programmer has or the application has is any data that's made it out safely to persistent memory. As we can see, we have only partially updated this array, and so it's basically inconsistent. We've lost the value of x forever, and we have the value of y redundantly in two locations. This would be a nightmare if it were not for the wonderful log that we've kept around, and we can use it to revert back to an older and but consistent state. And so we revert the value of y back to x, and this is a stale value, but this is a consistent location. And so this is something that the application can work with. So this is great. Yeah, question.
How do you relate that to the line of code
That's a very good question, but that's also a separate issue. So that's kind of what I think Thomas talked about at the end of his talk, right? So what is the thread model for this, right? Do you restart from the same location, or the currently popular approach on PMDK is basically once you start up, right? You check the state of your array, you figure out till what point did you finish your computation, and you proceed from there. So to give you an example, let's say you have to do 1,000 iterations or some number of iterations of an HPC computation, right? You would store the iteration number also somewhere in the data structure. And so when you restart or recover, you would first read that value to figure out where was I in my computation and then proceed from there. But currently there is not much support for other programming models where you're persisting everything so that you know the PC or the program counter of the point where you crashed and then recover from that. Although I think Joe has some work where you can redo the last failure atomic, in the just do logging work. But again, there's very little consensus on what should the right programming model or the thread model be for recovery. All right. So we've used this STM, software transactional memory library. We are able to do something. But what I want to show you is that this is actually quite slow on real hardware. So this is some experiments that we've done on Optane persistent memory that was graciously given to us by Intel. So okay, on the x-axis, we have a set of data structures, including the ones I spoke of before. And we are doing either write or read or lookup operations on these. We also have two full applications at the end which use a map to perform different operations. And on the y-axis, we have execution time. And these bars are normalized so that the height of each bar is 1. Because we are not interested in the relative performance. We are interested in how the execution time is spent in these applications. So now let's break down the execution time into 3 parts. On the top, we have the time spent in logging. And a lot of transactional libraries that have come out in research are focused on reducing the time spent in logging. But I would argue that actually this is not really the bottleneck. The bottleneck comes in because of flushing operations that you perform. And that is where you see in the update heavy workloads, most of the time of the execution time is being spent. And at the end, you have the actual useful work in white, which is being performed to carry out the business logic of the application. So now, it's clear, if you want to improve the performance, at least for the update-heavy workloads, we need to focus on the cost of flushing and improve that in some way. So let's look a little bit deeper at the cost of flushing itself. So now, this is this wonderful micro benchmark on the left here that I will zoom in so that you can see. We perform a series of flush operations followed by a fence. And so this flush is basically your cache line write back on Intel, and the fence is an S fence. We're performing 16 of these in a row, and this 16 is just a number I made up for this presentation. Actually, it's a bigger one. And we plot the execution time, or the total time taken by this whole micro benchmark on this graph here. On the x-axis, we have something interesting. We have the fence to flush ratio. So it's how many flushes are you performing for every fence operation. And so currently, we are doing 1 flush for each fence. So that's the point we'll plot there. Each of these flush and fence combination takes about 350 nanoseconds on the Optane memory. And so 16 of these will take somewhere around 6 microseconds. Now, you can actually eliminate every fence, right? Every alternate fence, so that you're performing 2 flush operations in parallel. You are overlapping these flush operations, and you are able to reduce the latency by roughly a factor of 2. And you can play this game over and over again, right? You can overlap more and more flush operations with a single fence until there are diminishing returns towards the end, but it shows that there is this game that you can play where you're able to reduce the number of ordering constraints. And if you do that, you can overlap more flushes and get some benefits in terms of performance. Question, yeah.
Are these real measured numbers? 16 flushes per second?
Yes. Yep. So.
Really quick question.
Yeah.
Is that flushes on the same address or
No.
the address?
No, this is random address. If you flush the same address, currently there are some other overheads that come in and it would actually blow up, I think. But these are random addresses that were there in the L1 cache. So we pre-populated all of them in the L1 cache and then ran these numbers. So yeah, again.
What's the cost here? Because writing back 16 cache lines shouldn't be that expensive, right? Is it because of the cache coherence mechanism to make sure that you find the right cache line to flash back?
There are multiple issues here. Again, like we don't have access to the microarchitecture or and I don't work for Intel, so I don't know for sure. But some of our like hypotheses essentially are firstly, yeah, cache coherence is an issue, but probably not that much because like they are highly optimized. I think the media writes are slow enough, perhaps, that the queues that they have at the memory controller, fill up, and then you actually expose the cost of the media write to the program. Because remember, they guarantee that the persistent memory controller is actually persistent, right? Any data that makes it out to the memory controller will be flushed out. So you have to limit the amount of the buffer entries that you have there. But again, like these are all hypotheses that I have no way of confirming, but you know.
Did you try the same thing with multiple stores?
I think so. Yeah, we saw similar results even for that. Yeah, because even the non-temporal stores they do queue up at the memory controller. They just skip the cache coherence part of it. So yeah,
So it's really the fence is taking all the time, not the flush.
that's what my
With the flushes, it takes 1 microsecond, you do same number of flushes and the same number of fences, and then it takes 6 microseconds.
it seems like that, but the point is like if there were no flushes, the fence would finish in an instant, right? Because the fence is actually waiting for the flush. It's making the cost of the flush visible in the foreground of execution. So it's not right to blame the fences. But again, the key point here still stands, right? If we reduce the amount of ordering the only reason you require these fences is ordering, right? So if you reduce the amount of ordering that is required, you can overlap these flush instructions and get better performance.
Isn't the math is very simple. It's 350 nanoseconds times 16 equals 5 point something microsecond. You're waiting for the media. The media takes 350 microseconds. Actually, the writes are supposed to be slower.
No, they're about that, but that's still the fence, that's still the flush. The flush should write to the media.
It's
Yes.
asynchronous. CL flush is asynchronous. Fence makes you wait.
Okay, so I'm saying that you're saying I want to write, and then it says, oh, okay, now it'll do all the writes at one, but that still doesn't make any
No,
sense.
they'll all happen in the background until you hit the fence, and then the fence will wait for completion.
But then this should take the same amount of time as if you do a fence after each flush.
There
No,
are
because
multiple memory channels for one thing that can be written in parallel.
And these are all random cache lines, right? So there might be some amount of parallelism going on, right? And again, there is some serialization involved, which is why the diminishing returns comes in, right? And so actually what we found is this exactly follows Amdahl's law. And there's like 80 to 20%. So 80% of the flush is parallel and 20% is serial. And so, I mean, you can model this exactly with Amdahl's law. But okay, we can talk more at the end and I'll carry on for now. All right. Yeah, so our call to arms is clear. We must reduce the number of fences or ordering so that we can overlap more of these flushes. And the gains are so high that we can actually perform some more computation, right? If that is what we need to reduce the amount of ordering. So there is this trade-off that we can play. So now I'll get into how we actually do that with our minimally ordered durable data structures. And the key question again, how do we provide these nice properties of atomicity and consistency with minimal ordering? Well, if you look at the world of databases and file systems, there's been one technique around for a long time, and it's called shadow paging. You may have heard of it as copy on write, and all of them are similar things. And the key idea is we should avoid overwriting data. Whenever we overwrite data, we need to perform some logging or some dependent operations, like the ones here, and we need to order these log entries or the log writes before the corresponding data writes. So that introduces these fences and ordering constraints in the code. And in this one transaction itself, we have 4 flushes, but we also have 3 fences. So we are not able to overlap a lot of these flushes. So instead, what Shadow Pages recommends is to perform out-of-place updates. And so I'll give you an example of how that works. So once again, we have the same example as before. We have an array, and we are trying to swap 2 entries in this array. We don't have any logging anymore. So instead, what we do is we create an entire copy of this array, and we call it a shadow. All of the updates that we wanted to perform, now we perform on this shadow. And we don't really need to take any precautions here because we still have the original array with us, right? We are not modifying it in any way. So once both the updates are performed, we simply flush out the entire shadow out to persistent memory, have a fence there to make sure that the flush actually completes. And then from this point on, the application will use this new updated version because it knows it's durable, consistent, and it has been done atomically, and it will proceed. So again, if you look at this code snippet now, we have just one fence, so just one ordering point. But we've added some new things now, right? We've created this entire copy of the array at the top, and we've flushed out the entire copy of the array at the bottom. So you've taken, okay, question.
Do you stuff like multi-threading?
What?
Multi-threading and fencing multiple objects, multiple threads running the same object into different fields.
Yes, we will talk about that at the end. So yeah, we've taken away the ordering constraints, but we've introduced a lot more, shadow paging constraints. And so to solve these issues, we actually found a good answer in the world of functional programming languages where the same issues come about, and they've already solved it. So we can reuse these answers. So okay, to give you a background, purely functional data structures are immutable. And what that means is once some data gets assigned a value, it can never be overwritten. So if I have a functional array and I want to perform a swap, I can never actually update any of the values in the original array. I have to create a new array with the updated values in place and then use that instead. Now, this seems horribly inefficient, and this is the same problem that we are faced with, right? But they have solved this problem in a very nice way. So if you look at functional data structures, the highly performant data structures are implemented as very efficient trees, and there are many examples of these data structures in the functional programming literature, and I've cited two here. And the way these work is even contiguous or conventionally contiguous data structures like vectors or arrays are implemented as trees. And so what we can do is we can have two copies of the data structure which are logically a copy, but in actuality they both reuse over 99% of the internal nodes of the tree. And so when you create a copy of this data structure, you're writing or allocating a minimal amount of data that is needed to separate out to actually implement the updated operation. And so this reduces the overhead significantly because now you have two copies, but physically the data is mostly unchanged. And so these class of optimizations are called structural sharing optimizations, where you're sharing the structure of the tree between different versions of the data structure. Implementations are found for these, for most common data structures in most programming languages at this point, because the functional programming research literature has been at it since about 2000, so they have done a lot of work in this regard now. And so yeah, our idea is basically simple. We are calling it functional shadowing, where we use shadow paging to reduce the ordering constraints in our persistent applications, and we use all of these optimizations from functional programming languages to reduce the new overheads introduced by shadow paging. In fact, we have a recipe to simply repurpose these existing functional programming data structures to build our minimally ordered durable data structures. So the first one is easy. You just find efficient functional implementations in the language of your choice. And I have found ones in C++, which I'll talk about in a bit. And there's also things in Java, Python, and a lot of other languages. You pick a persistent memory allocator, because remember, we want to allocate all of our internal nodes all of our data in persistent heap as opposed to the volatile stack. You have some more, there are some other smaller things that you need to do, but a lot of it can be done in a procedural manner as opposed to thinking about each of these updates that you're doing. The main change is that you need to ensure that any update operation, so like a pushback in a vector or a delete, you have to flush out any of the modified cache lines in this, right? And this is actually quite easy with these data structures, because if you think about it, the data is immutable, right? So the only data that you've touched is data that was newly allocated in this operation. And that is the only data that you need to flush out. So once again, you can do this in a very simple manner without inserting any fences at any location. So for each failure atomic region, you just look at what data was allocated in this region and flush it out at the end with overlapping flushes. And yeah, at the end, you have a minimally ordered and highly performant data structure, which you can use to your heart's content. We also have tools that we've built around these, because there are a lot of simple steps here, but it's hard to get things, it's easy to get things wrong, right? So we've used PMEM Valgrind, which the PMDK developers have put out, to sort of automatically figure out what cache lines are being touched, when are they being updated, when should we add fences and flushes and so on. to make sure that we've actually done this right as opposed to missing, things here and there. So now very quickly, I'll go over some of the use cases that we have and show how we've implemented some of these. So for a very simple use case, like performing a single update to our data structure, like adding something to a set or a map, we can expose a very simple interface that I will show you. But for a lot of things, programmers also want to perform multiple updates to the same data structure. And this is the swap example that we saw, right? Where we perform 2 updates to the same data structure. And you want to ensure that it's failure atomic, consistent, and durable. And then composability is a big part that's not talked about enough by researchers who handcraft these data structures, where we want to ensure that we can take something from one map, insert it into another, and do this in an failure atomic manner. So we handle that case as well. So let me get into these. And using an arbitrary combination of these, you can create as complex a code as you would like. So the simplest one is performing a single update to one data structure, and we have these update operations. So depending on the kind of data structure it is, we support most STL abstractions for it. We have functions which perform the update atomically, durably, and consistently. And this is all that the developer sees. So there is no logging, no transactions, no fences and flushes. The actual data structure is a black box, which if you see, it's just some kind, a modified functional data structure on which we perform a pure update. So we are not, modifying any of the original version of the tree. Once all of the data has been flushed out asynchronously, we have a fence to make sure that all of it is durable, after which we can swing a pointer to point to the new version as opposed to the old version. We need to make sure that we reclaim memory which belongs to the old version, and so we do that with a combination of garbage collection, which once again is mostly in place in the original functional data structure. So there is very little work that you have to do to move these functional data structures to durable and persistent data structures. For performing multiple updates to one data structure, we have to expose some of the details, including versioning to the programmer. But again, it's still simple. The way this works is the programmer would perform an update, and they get returned a new version of this data structure on which they perform the next update, and so on and so on. And at the end, we have the simple commit API, which takes in the original data structure as well as all of the newly created versions, reclaims the memory belonging to all of the intermediate versions, and updates the data structure pointer to now point to the latest version. And so at the end of this commit step, the application is guaranteed to have a updated, durable, and consistent data structure. And before the commit step, they are guaranteed to have a durable and consistent data structure, which is the old version of the data structure. So at no point in this entire process does the data structure become inconsistent.
Yeah, but isn't that much less efficient than applying both updates to DS shadow 1 and then simply exposing it? Why make a second shadow?
Yeah, that's a very good point. We have some optimizations for that as well, but we didn't want to bring that in here because not all functional data structures have been designed to support that. And so we wanted to stick to what we can do right now without multiple modifications. But yeah, for most simple data structures, we actually have that in place, where anything beyond the first shadow, you don't need to perform out-of-place updates, right? Because the programmer can just discard that if things go wrong. So you can perform all of the next updates on the first shadow itself. But yeah, that's an optimization that we do for some data structures. And then similarly, we have another API for the same kind of stuff where you want to update multiple data structures atomically with respect to each other and with respect to failure. But this time the commit step, although it looks the same to the programmer, is implemented in a slightly more complicated fashion, because we have to swing multiple pointers now to point to the new versions of the data structure. And so for that, we currently fall back to a transaction. But this is a very short transaction because we are only updating a single pointer or a few pointers. So there are more ordering points, but it's a short transaction. Once again, for a lot of cases, we've observed that you can actually avoid this transaction altogether by rolling up the updates and performing the functional shadowing at a higher level. So if you have the same, if you have an object that holds 2 maps that you're trying to update, you can replace the object with a new copy of the object as opposed to performing this transaction. And that is what happens in a lot of programs where you have a durable root or something, so you roll up the updates and perform it. But for the general case, the transactions should suffice. We have some open questions where, how do you do concurrency, which is a big problem in this field right now? Do you use locks? Do you use something else? For our out of place style updates, I think read copy update is a good match, although it requires some more complicated analysis on how do you get exactly right. We need to ensure that there are no memory leaks. Currently, there are cases where the allocator could lose some newly allocated data in case of a crash. And then, yeah, there are many other optimizations that can be done, such as batching updates, performing in-place updates on the shadow itself, like the gentleman there suggested, and so on. I'm going to run a little bit quicker now because I think I'm out of time. I'm not sure. Oh, okay. Nice. Evaluation. So we use the C++ library of functional data structures to build our mod data structures out of. We use an off-the-shelf persistent memory allocator, and we compared against Intel PMDK. That's what the results earlier were, right? The graph that we saw with the different data structures, that was from Intel PMDK version 1.5, which came out late last year. And I think since then, the performance of PMDK has slightly gone up, but the main performance patch was in 1.5. So after that, I don't think they've done too much in terms of performance. PMDK uses hybrid undo redo logging, and they have a ton of optimizations in place to make the transactions as fast as possible. And so I think that's a fair comparison. So again, this is the same graph as before, right? I've just changed the colors to make it homogeneous. And I've added a new bar now here, which is our mod, the performance of our mod data structures. On the y-axis, we have execution time, and so lower is better. So one common observation that you can make is we've gotten rid of logging overheads completely because there is no logging. For most update-heavy workloads, we have reduced the amount of time spent in flushing, although we do perform some extra work, right? Because we have to create, allocate some more data and flush out some more data. So the time spent in other useful activities has gone up slightly. In the case of vectors, we do not perform as well as the baseline because, or the array, because the arrays is a very simple data structure to optimize for a transaction. There's basically 2 or 3 cache lines that they are writing out in the transaction, whereas we have a level of indirection. So we add more overheads than we can take away. We still perform close to it, but we cannot beat the baseline vector. But in any case, we have a way to sort of reuse a lot of these optimizations that have been done in functional programming data structures and directly use them for our benefit. And one place you can see that is in the read mostly workloads where, because the underlying data structure itself was optimized to have a highly cache conscious layout and perform as little misses as possible, we simply get the benefits of that for free because we are not using a general, a queue or a stack. We are using these highly optimized functional data structures for free. And so we can enjoy the benefits that they bring about.
So why is the read on a vector so much more efficient in your system? You changed the array into a tree. It should be slower, right?
So the problem here is the baseline for the vector. I mean, in terms of a write, it's quite fast because they are not doing too much. But for a read, there is some level of indirection even in the baseline vector because you can grow. These are dynamic arrays, right? These are not a static array, and that's why there is some level of indirection there. Yeah, but you have the base still points to, like, there is a level of indirection so that you can point to the new base of the root. Again, you're thinking, so these are efficient trees and they do a lot of analysis. So they are not very deep trees. They are usually broad trees so that you can limit the amount of data that you copy. And they use things like path compression to limit the height even further. And in some cases, we are also, for the read side, we perform much fewer instructions than the baseline as well. And so that is where we gain some of the benefits. For transactions, one reason that the read is slightly higher is because we wrap all of these operations in like transactional semantics or in a failure atomic region, right? So you still have to track the fact that you read this location. So that adds some extra overhead. Does that make sense? What? Yeah. Yeah. For both of them, I mean, we perform all of these in a failure atomic region, right? So PMDK tracks the fact that you've read this location. So
If you're just doing reads, you wouldn't need a transaction region on it. I mean, if all you're doing in your region is reads, you don't need a transaction region at all. I mean, I'm not, that's not.
no. Yeah, that's true. Yeah.
That would make a difference in this also.
Yes. Yeah. So I want to actually move from this kind of an evaluation to simply showing like a traffic, because I think that's going to be more representative, where we do like 80% reads or 20% writes or something like that, because that would actually require you to do, something more sophisticated. So yeah, we are still trying to figure out what is the best way to, compare these. And again, we need to probably have more applications. But thing is, there are very few persistent applications right now which use like a stack or a queue beyond just simply pushing and popping things off a stack, which is very contrived if you think about it. Also, lastly, there is some weird corner cases because of these functional data structures. So for the fact, in the queue pop example, you see there is a highly deep recursion that takes place in one of the cases that blows up the execution time. So if you actually have a mix of both push and pop, right, it goes away. So which is what we show in PopStar. If you only perform a pop after a million pushes, it performs a million deep recursive lookup, which blows up execution time. So yeah, you have to be conscious about some kind of these pathologies. Okay, so to summarize, we've created a library of recoverable data structures, and we've essentially showed a way to create new libraries using existing implementations of functional programming data structures. We have improved performance by reducing the number of ordering constraints in these software. We use functional shadowing instead of software transactional memory for the most part, and we offer some performance improvements over current STM. Thank you, and now I'm open for questions.
So with something like a vector, when you move to this functional data structure format, now your memory is fragmented due to the fact that it's a tree. In other words, it's not a flat, even portions of it aren't flat. So I just wondered about implications for compute intensive, so like you can't use Cindy units anymore, and just in general, you're using your data structures in many different ways, and would you recommend copying them to standard data structures before doing that, or how would one approach that problem?
So once again, the whole vector may not be contiguous, but these data structures are they use highly broad internal nodes. So you can fit nodes, several nodes into one cache line. And so you can still perform these kinds of optimization, just not at a higher, like a 1 million node granularity, perhaps. There's still a lot of contiguity in the internals of this vector. So you can still use, let's say, 64 wide, SIMD accesses to get them. Does that make sense?
It does make sense. I'm not sure how a compiler would be able to figure that out, but I mean.
Yes, yeah, that's.
What you're saying doesn't make sense.
There are some, like at least in C++, like 11 onwards, you can have some align, keywords in that to explain your intent to the compiler at least, and maybe that will help. I don't know exactly how the Intel compiler auto parallelizes a lot of these things. So.